So let's discuss the special case of the projectile motion. Now over here we have a projectile which is already at some height above the ground. Say for example, this height above the ground is h. Now this projectile is being thrown horizontally with respect to the ground. So the initial velocity is parallel to the ground. Now in this particular case, we need to find out the time of flight, we need to find out the range and so on. So this would be our range. Now the ball after some time would be reaching over here, after some time over here, and finally the ball is going to reach, right? So we are going to adopt the similar analogy that if I place a light and when the ball is over here, at that time is 0. When the ball completes its journey here, the time is equal to time of flight. Now in this situation, when you turn on the light, what is going to happen? The shadow of the ball on y-axis is here itself. When the ball reaches over here, its shadow is seen here. When the ball reaches here, its shadow is seen here. When the ball finally touches the ground, the shadow is seen at the bottom of the building. So the shadow travels downwards and the displacement of the shadow is equal to the height of the building, and this is a one-dimension motion along y-axis. In the same way, when the ball is here and if I place the light source in this manner, then the shadow is seen here on the x-axis. When the ball reaches over here, its shadow is seen here. When the ball reaches here, its shadow is here, and the ball and the shadow finally reaches over here. So again, from time 0 to time of flight, the shadow travels a linear distance along x-axis that is equal to the range, right? Now we can apply the equations of motion s is equal to ut plus half at square for both, because now they are both traveling in one dimension. I'm talking about the shadows, right? So now let's apply this equation for the shadow which is moving along the x-axis, sorry, the y-axis. So I'm going to say that this is equal to minus h, that is initial velocity. Okay, let me clarify that this is, I'm going to apply this for the y-axis, uyt plus half a y e square. In the previous section, we have discussed that all vectors which are in the downward direction will be taken as negative. So the shadow of the ball was here, shadow of the ball reaches over here, it travels along negative y-axis because this is the origin, right? So the displacement is equal to minus h. You can only use y symbol under the vectors, not for the scalars, right? And this uy is 0. That is due to the fact that initial velocity is purely along x-axis. There is no component of velocity along y-axis. So I must say that ux is equal to u and uy is equal to 0. So times t plus half times acceleration on the ball anywhere is along the downward direction, and the downward direction vector is taken as negative. And I'm going to substitute time of flight over here because finally the ball reaches here and the shadow reaches here. The time is same for both of them. So I should mention minus h is equal to, this is gone, minus half g t square, minus minus cancels. I must say 2h by g times root is the time of flight. This is our first equation. All right. Now, if we are being asked to find out the range, this is our first equation. The second equation is the range, and now I'm going to target the x-axis. So sx is equal to ux t plus half a x t square. Now I'm going to use this equation for x-axis. So the shadow of the ball goes like this. When the ball reached from here to here, time of flight is the time taken for both. So here I'm going to say range, which is positive because it is along this direction. This is the displacement. So the shadow moved from here to here, positive displacement. Ux is u. The entire vector is along the x-axis, u, and this is time of flight plus half. There is no acceleration along x-axis. times t square. So from here we get the range that is equal to u times t. This is our equation number 2. Now what we can do is we can substitute the value of this time of flight, that is under root of 2h by g, and we will get our final answer. So if you don't remember the results, you can just derive it. It's a matter of minutes. Now the last part of the equation states that we are supposed to find the equation of the trajectory. The equation of, so basically we are supposed to prove that this is not an equation of straight line. The body is not traveling in a straight line. The body is traveling in a curved path. So what am I going to do is, I'm going to say that at any point, say for example P, when the ball reaches over here, the x, there is some value of x and there is definitely some value of y, right? Where x and y are basically sx and sy. So over here sy is basically y and sx is x, because when the shadow of the ball reaches over here, this distance is what is sx or x. Let me clarify that the shadow of the ball like this and this, from when the ball travels like this, the shadow of the ball travels like this. This is sx. At the same time, when the ball goes from here to here, this is sy. But here I'm simply going to use this as y and this as x. So we get the better idea, right? So the first thing is x or sx is equal to ux t, because ax goes off, ax is 0. So I'm simply going to write down x is equal to ux is simply u, and at any time when the ball reaches over here, time is any time t, right? So we get the first equation. Now the second equation is of the y. So y or sy is basically, I'm going to say sy. So sy is equal to uyt plus half ay t square. So y is equal to uy 0, so this term goes off. That is equal to minus of half minus g times t square. Okay, now what am I going to do is I'm going to find out the value of time from here and substitute here. So our equation becomes y is equal to minus g by 2. Now t is x by u square. So what do we get? Y is equal to minus g by 2u square times x square. Now you can very well see, guys, that this is not an equation of straight line. This is an equation of parabola, right? So our path is parabolic and the trajectory is parabolic in nature.